Hey guys, welcome back to Food for Thought Physics. Last time we defined three important kinematic quantities, and these are going to be position, which we called x, velocity, which we called v, and acceleration, which we called a. And we've related these three quantities with these equations here. So we said that velocity, for instance, is the derivative of position with respect to time, and acceleration is the derivative of velocity with respect to time. And we can reverse these equations here by saying that position is the integral of velocity with respect to time, and velocity is the integral of acceleration with respect to time. And so what I want to do here is first take a closer look at what this derivative and this integral really mean. So we covered this a little in the last video, but I feel like I didn't give a clear enough explanation of what these really are. So let's look at the derivative first. So here we have a graph of plotted the position against time. So we have some random position function here. So if we take any 2 points on this position function, let's just take the starting point and this ending point over here, and connect them with a line, then we're going to say that the average velocity between these 2 points is going to be actually the slope of this line. So we're going to write that as v with a bar on top, if you remember. And we can find the slope by doing this. If we create a right triangle like this, say, it's not really a right triangle, but if you imagine this is a right triangle, then, well, slope is just rise over run. And we can see, well, this rise here, that's just going to be a change in x, right? The final x minus the original x. So this change in x we're going to write as delta x. The Greek letter delta means change, usually. And this run here is just going to be the change in time, or we're going to write it as delta t. So our average velocity is the slope of this line. That's going to be equal to delta x over delta t. And however, our definition of general or instantaneous velocity here, the derivative of x with respect to time, it's not this average velocity, it's the instantaneous velocity at any given point. So we can think of it like this. Instead of thinking as one given point, imagine we zoom really, really far into the graph and connect two infinitely close points. Say this point and this point. Obviously, these points aren't infinitely close, but we need this for sake of drawing. So we have these two infinitely close points. And we're also going to build a similar right triangle, like this. Right. And so, since these 2 points are infinitely close, we can think of them as the same point. And the slope between these two infinitely close points is just going to be the slope at that one single point. So we want the slope of this small thing here, the average velocity between these two infinitely close points. And that's going to be our instantaneous v. And so, well, here we see there is a change in x, but it's going to be infinitely small. We call this a differential change. I'm going to write this down. Differential. And differential just means infinitely small. And so here our changes in x and t are physical changes, as in they're measurable, they're large. So this differential, a differential change is going to be infinitely small. That's what differential means, infinitely small. So we have this infinitely small change in x, which we're going to write as differential x, or dx, and it's accompanied by this infinitely small change in t, which we're going to call dt, differential t. And so if we take the average velocity between these two infinitely close points with infinitely small changes, we have v equals dx over dt. And this here we see is the same equation as we have up here, v equals dx over dt. And this is what this d here stands for differential. It's an infinitely small change. And you can see why this equation here for v is similar to this equation here for average v. The only difference is that for average v, we have a physical change in x over a physical change in t, while for instantaneous v, we have a differential change in x over a differential change in t. So we just zoom in really close and take in these 2 points, these infinitely close points with infinitely small changes. And we get this instantaneous v here. So I hope that sort of explains what a derivative is, at least. Now on to the integral. So, as we said, an integral is defined as the area under the curve, and it is the amount of change in something. So, for instance, we said position is the integral of velocity with respect to time. That means that the change in x from, say, this point to this point is just going to be the area under this curve, from this curve all the way down to the x-axis. And so, without calculus, finding the area under these curves is kind of difficult. Obviously, we can't just add them up. We can't just use some simple geometric formulas for this. However, what we can do is we can use these rectangles here to approximate that area. So say we have this rectangle, and say we have this rectangle, and they really shouldn't meet, so I'm going to make them meet. So we say we have these two rectangles approximating the area from here all the way to over here. And what this is called is called a Riemann sum, or a Riemann approximation. I'm going to write that down. Riemann sum. And a Riemann sum is just an approximation of an integral. We might not be able to find the exact area under this curve right now, but what we can do is use these rectangles to sort of approximate the area. So if we think about it, if we if we draw this line over here, basically, then instead of the area under this curve, we'll use the area of these two rectangles. And we can see, well, there is some gap here, but it's not that large, so we have somewhat approximated the area. And well, let's find the area of one of these rectangles. So let's assume that these two lengths are the same first. Let's just assume we'll use some number of rectangles, and this length is just going to be a change in t, or a delta t. And this length here is also going to be a delta t. Well, the altitude of any given rectangle is just going to be v at whatever point on the left is. We can also connect them on the right, but like let's just do left for now. So we have v of whatever this v is at this given point, and whatever v is at this given point. So the area is in here. We're just saying the area is equal to v delta t. And so if we want the area of the entire Riemann approximation, that's just going to be the summation of every v delta t from wherever to wherever, right? So we're going to sum however many rectangles we have. And the reason I say however many is we don't need to use 2. As we can see, this 2 is not that great of an approximation. We have these massive gaps here. What if we use, say, 4 rectangles? Say a rectangle here, a rectangle here, a rectangle here, and a rectangle here. And we can see, well, these 4 rectangles, well, wow, we've used up some of this gap here that we see. These gaps are now a little bit smaller. We have 4 gaps, but they're all now smaller. We've taken some of that area in the gaps and filled them up with a better approximation, basically. And now we have 4 rectangles, so the delta t is going to be divided by 2. But it's still always going to be the summation of every v times delta t there is. So we can imagine, well, what if we use more rectangles? The more rectangles we use, the more these gaps are filled, and the closer we get to the actual area under the curve. So say we have this infinitely thin rectangle here instead. And the idea is if we use many infinitely thin rectangles, we can have the exact area, right? And again, I can't draw this as infinitely thin, obviously. But let's just pretend this is infinitely thin for a second. Well then, what is the area of this rectangle here? Well, the height is still going to be a v, but this the base is going to be different. Instead of a delta t, a physical change in t, since it's infinitely thin, it's now going to be a differential change in t, or dt. And so the area of this rectangle is going to be area equals v dt. And we can see, well, this v dt here is, we see it up here in this definition of position equals the integral of v dt. This integral symbol here just means an infinite sum. So when we take an integral, that's just adding up all of the tiny v dt's throughout this entire curve. So we can imagine putting infinite number of these infinitely thin rectangles here, all with area v dt for whatever v and that is, and some infinitely small differential t. And we're adding them up with this this long s here, and that this integral symbol just means infinite sum. So we add all those up, and we should get the exact area under the curve.